Good evening. In this video, I want to cover networks in a fairly high-level way. I don't want to go too deep into gritty detail, but I do want to give some semi-realistic examples of how networks operate. The Internet, as we now refer to it, is the largest public network of computers. It's accurate to say that on the Internet, all machines are able to access each other. Now, this is not to say that all machines can get access to each other. We have various protections against that kind of thing. But if a machine is willing to accept a certain type of connection, there's nothing stopping another machine connected to the Internet from doing that, provided it does it correctly. Now, what does it mean for two machines to be connected to each other via the Internet? If we imagine a simple example of two machines that want to send messages to each other, these two machines can set up a direct link between each other and pass messages across that link as much as they want. And this is a point-to-point network. It's also extremely uncommon to have two machines directly connected to each other. When your network gets to a certain size, it becomes infeasible. Because if we added a third machine, C, you'd have to have two more connections. If you add another machine, D, you now need even more connections. And if we add more machines, the number of connections required goes up very quickly. And it becomes a bit of a mess. So typically what happens is there is some piece of network hardware sat between the machines. That all of the machines talk through. And this would be a router, and its sole job if A had some message that it wanted to send to C, A would send that message to the router would inspect the message and see that it was destined to go to machine C, and it would deliver it to machine C. So it acts as a kind of intermediary between all of the devices connected to it. And that works well for local networks. You will see this model deployed in schools, homes, businesses, and so on. If you have a Wi-Fi network at home, for example, your Wi-Fi access point, your Wi-Fi router, is performing this job for all of the devices on your local network, and it works well. It gets a little more complex when you say you want to access some machine that is not in your local network, which is the normal kind of mode of operation. It's not often you try and access devices directly on your local network these days. So when that happens, let's encapsulate everything we had on that page down to here. Router and various devices connected to it. Now let's say we have a device over here that represents some popular website. We will call it F. And F is somewhere on the internet. So it's a big cloud representing the big public internet. It's big and scary. You need to be able to send a request destined to F to your router, and somehow it ends up there. But how does it work? To explain how it works, I'm gonna hark back to a favorite example of mine when I'm explaining this to people, and that is the rail network. This works equally well with flight networks. And these aren't some obscure network technologies. I am actually talking about trains and planes. So in the UK, this is a rough depiction of the UK. We have major rail hubs in London, the kind of Manchester, Liverpool area, Scotland. There are some in the Midlands as well, but we have these big rail hubs. Loads of trains go through these, and there are typically routes between all of these. Maybe you'll have some direct route between these two as well. And the major hubs connect to each other, and they have lots of rail lines, really high speed, that move between these big major hubs. Then maybe you'll have some smaller, more kind of like town railway stations dotted around the country. And each of these will have some link to the big hubs, maybe multiple big hubs. And you end up with this kind of hierarchy system where you have really big fat pipes between the big hubs, and you'll have smaller rail lines between more kind of regional, local railway stations. And this is how we transport many millions of people every year on the rail network. And computer networks operate in much the same way. We have big hubs of connected devices with huge amounts of bandwidth, and then we have smaller hubs, except we don't call them hubs, we call them hops. So your router or router, for any Australian viewers, will connect into some large hub. These are typically operated by quite big internet providers. So one of the major ones is called Level 3. So maybe you'll have some indirect route into one of the big hubs, and then that will have some indirect route to F, and your message will travel through each of these hops until it gets to F. When it gets to F, the thing that you're asking for, maybe it's some social media page or a video of a cat, then you'll receive it back, often via the same route, but not necessarily. And that's kind of that's the structure of things. You have a hierarchy with larger nodes. We call those exchanges. smaller nodes called hubs and connections between these things. And they're all physical connections. That's something I think that surprises people. So even going across from the UK to America, across the Atlantic, for example, there are cables, like really, really long undersea cables. And I don't think people realise that, but they literally just wash up, like in beaches, right? Like you could be walking along a beach somewhere and you'll just see a big cable coming out of the water and going under the ground. And most people won't think twice about what it is, but very often those cables are network cables connected to the other side of the ocean. But how does your router know where to go? How does this network actually get constructed? So I imagine some of you would have seen an IP address before. IP addresses a sequence of 4 numbers, each what we call octet, because there are 8 bits in each of these sections, so between 0 and 255. So whenever you're watching a film or a TV show, they show a bunch of IP addresses, and they have crazy numbers in them, like 824.0.1.300. Like, those things are obviously fake. The maximum that any single section can be is 255. So IP addresses are basically numbers, and they're represented as 4 individual numbers, just to make it slightly easier for humans to remember. This one here is special. It is called the Loopback Address. And it always refers to the current machine. So if you send a message to 127.0.0.1, it will come back to the same machine. A more kind of realistic address might be something like 98.2.0.41, and this is just kind of off the top of my head. I don't know if that's a real address. It probably is, because most of the IP address space has been used now, and that's a topic we'll get onto in a bit more detail later. But computers use these 4 sections in a very similar way that we do. So in your router there'll be a bunch of rules. Your router will know, for example, that it will have the IP address for each of the 4 things connected to it, and if you ask for something that isn't one of those 4 things, it falls back to a default route which goes deeper into the network, the internet, called the default gateway. And then the next step here will have similar rules. It'll have a bunch of devices connected to it, and those devices will tell it, I know the locations of these devices with maybe this thing here knows about 2 devices. And those devices say, hey, any IP address you get that starts with 101.10. whatever, send them this way, because I know where they are. And then this one over here will say, hey, if you get like 242.8.1.6, I have that address, so just send it here. Other than that, this node will have a default gateway as well, and it will go into this bigger node. And that's kind of how it works. Each node has an idea of which addresses it can route to correctly, and if it has a message with that address, with an address that it recognizes, it'll just send it in that direction. And that really is kind of it. There's not much more complex stuff going on than that. The actual way that routes get discovered in the internet is a bit more complex. But in principle, it is a set of nodes, and each of these nodes is just another computer. There's nothing special about it. Your laptop can be a node in this network that routes to other nodes. There's really no magic involved. It's just nodes that have rough ideas of where to send messages, and then eventually those messages get there. And that is how our internet works, you know. This is all these addresses, are part of what's called the Ipv4 Protocol. Now, let's just write this out a second. In the Ipv4 Protocol, addresses for machines are 32 bits. That's 4 times 8, that's 4 octets, so is 32 bits. Now, 2 to the power, whoops, muscle memory taking over. 2 to the power of 32 is a little bit more than 4 billion. And back when this protocol was first designed, in part by a famous computer scientist called Vince Cerf, the belief was 4 billion is way more than we'll ever need. Like, this project started way back in the 70s. In its first incarnation, they called it the Arpanet, and it was just meant to be a very small network between universities for sharing research and sharing data and stuff like that. Never ever did they anticipate how successful it would be. And here we are today, 2018. We have very much used all of the addresses. We have run out, pretty much. We have started resorting to doing terrible things in order to squash address ranges. Way back in the day, every device that was connected to the internet had a unique IP address, but that's not so true anymore. For example, mobile phones, when you connect to the internet via your cell carrier, you will be behind what's called a NAT gateway. So NAT gateways typically have hundreds, maybe even thousands of mobile devices connected to it, and this NAT gateway will have one IP address. And it will kind of demultiplex or squash all of these devices to make it look like they're coming from the same IP address. And this is simply because we just don't have enough IP addresses to give every mobile device an IP address. The NAT gateway is responsible for keeping track of which phone requested what, and when responses come back, it tries to match up the response with which device should have asked for it. It's not always successful. It's sometimes this can cause your request to get lost if the gateway can't figure out which device requested it. It can also cause other problems, like, for example, schools get this quite a lot, where, have you ever tried to do maybe a Google search or something like that, and it's asked you to do a captcha, like it's asked you to fill in what the difficult to read letters look like, it may have said something like, we suspect malicious activity from this IP address. And the reason is, sometimes schools have net gateways as well because they operate a large number of devices and they can't afford to give them all IP addresses. I say afford, and I actually do mean afford. They can be quite expensive, and I'll talk more about that in a second. But they'll use a net gateway to save money, and to Google it just looks like one person issuing tons and tons of searches really quickly, and it ends up looking malicious, as if they're trying to attack Google in some way. So overall, NAT gateways aren't very nice, but they're a solution to the problem we have of running out of Ipv4 addresses. There is a slightly better solution, and that is Ipv6. And in Ipv6, instead of having 32 bits for the address, we have 128 bits. So how many devices does that let us have? Well, it's a lot. I'll write the number down. It is yeah, it's a pretty big number. I'm gonna try and say it. 340 undecillion, 282 decillion, 366 nonillion, 920 octillion, 938 septillion, 463 sextillion, 463 quintillion, 374 quadrillion, 607 trillion, 431 billion, 768 million, 211,456. I think it's safe to say this time around that should be enough. But IPv6 is a little bit more than an increased address size. They are trying to fix a number of other problems with networking, and if you have interest in networking, I highly recommend looking it up, because it's a little bit too detailed to get into in this video. So a few moments ago I mentioned that some schools can't afford the IP addresses. In the beginning of the internet, we allocated quite large chunks of the IP address space to certain companies. We typically break an IP address up into two parts. We say that there is the network part and the host part. So 32 bits. You could say, for example, that the first 8 bits represent some network, and the remaining 24 bits represent an actual machine on that network. And this would end up being quite a large network. 2 to the 24 is in the region of 16 million devices. We ended up coming up with 3 types of IP address. We would have networks where the first 8-bit, IP addresses where the first 8 bits represented the network. We would have IP addresses where the first 16 bits represented the network, and IP addresses where 24 bits represented the network. In practice, it doesn't make a huge difference. You still have 4 billion individually routable devices. It just gave us a way of thinking about networks and how to allocate those blocks to companies. So we called these Class A networks, these Class B networks, and these Class C networks. And this was quite wasteful. There were only 256 Class A networks to give out. There were 65,000 Class Bs, and there were 16 million Class Cs to give out to organizations, companies, and things like that. As the internet grew larger and larger, this very coarse logical separation became, it ran out basically. There's no other good way of putting it. So this logical grouping of blocks of the internet was referred to as classful routing, because we had Class A, Class B, and Class C networks to represent networks of different sizes, organizations of different sizes. We ended up replacing that some years ago with a thing called CIDR, or CIDR, which stands for classless interdomain routing. I should capitalize that one. And the only real difference, all of the address scheme stayed more or less the same, except we, instead of having 3 different classes, we had a different class per bit. So we started writing the size of networks as /16/8/24. This just means that this is the number of bits used for the network portion of the IP address. And it gave us the flexibility to have networks that was, say, /28 or /31. So we were able to give out more fine-grained networks and open up the networking for smaller companies and things like that. Actually, the more I think about it, the more I realise I made a small mistake earlier. Actually, kind of a big mistake. I mentioned that it's only really a logical grouping, and it doesn't actually give you more network space, but it does also give you more network space. If you can imagine, we had a /8 address, and we would normally write that as, say, 10.0.0.0/8 is a network, and it starts with 10 in the first 8 bits. And then let's say we had 10.10.0.0/16. These are 2 distinct networks, but we are able to reuse the 10 in the first position, provided we say that it's a /16. So just because somebody has 10/8 doesn't mean that we can't prefix /16s with 10. So we do end up with more network space as a result, because we have this designator here that says the network size. It does mean that the actual inner part of the network can only be of a certain size. So in a /8 network, you can have 2 to the 24 devices, and in a /16 you can have 2 to the 16, because you do only have a fixed size inside of that to play with. That was a rather large and windy detour into IP addresses and network structure, and you might be thinking, I have never seen any of this. I've never really touched an IP address. This is gibberish to me. What are you talking about? How did you get in my house? And so on. And you wouldn't be wrong, but under the hood, these IP addresses are how machines find each other. But humans don't use them. We use things like www.youtube.com, and this is called a domain name. Because it's easier to remember youtube.com than some arbitrary set of numbers. Numbers work really well for computers, but remembering billions of different numbers is not going to work for human beings. So over the top of Ipv4 and Ipv6, we built what is called DNS, or the domain name server. And DNS is very simple. Its entire job is to take this and convert it into an IP address, e.g. something like 16.20.16.1. How does it do this? Well, in pretty much every computer now, there will be some configuration that tells it which domain name server to use. Now, most internet service providers will run their own domain name servers, but there are a few public ones run by other companies that you may be familiar with. Domain name servers can't actually have domain names themselves, because that wouldn't make any sense. You can't ask a DNS what a domain's IP address is. So you can't resolve a domain name unless you can talk to a DNS server, and you can't talk to a DNS server with a domain name, because it's just a circular dependency, right? Like if somebody had dns.com as that domain name server, and you configured your PC to use that, your PC would be trying to ask this what its IP address is in this infinite loop, and it wouldn't work. So all DNS servers have to have bare IP addresses, which is why they try and choose easy to remember ones. For example, Google have 8.8.8.8. They also have the lesser known 8.8.4.4. And recently a company called Cloudflare released their own public DNS server, and they released it on 1.1.1.1. Now, hilariously, they had a bunch of trouble with this. A lot of network and system administrators use 1.1.1.1 as a kind of dummy testing address. So this DNS server suddenly, as soon as it came up for the first time, it was just kind of bombarded with junk, meaningless traffic from people that have been using this address for ages and expecting it to go nowhere. I thought that was really funny. So assuming your PC has a domain name server IP address configured, if you were to visit www.youtube.com, let's say we have our PC here, our router here, the internet here, our DNS server over here, and YouTube over here. We say that we want to go to youtube.com, and to do that, first we need to go to the DNS server. So we say to our router, look, we have this message for the DNS server, and the router's like, okay, the DNS server isn't connected to me, so I'm just going to default gateway this into the internet. And the internet works some magic using that rail network-esque hierarchy that we described in some depth earlier. It ends up eventually at the DNS server, and the DNS server replies to us with the IP address for YouTube. Once we have that, we use that IP address to find our way to the YouTube servers. And then at the very end of this, we get to watch videos of cats. Because why else do you use YouTube? That looks more like a mouse, but yeah. You get the idea. And this happens for pretty much every website that you want to visit. The first thing your PC always has to do is called a domain name resolution. So if you visit a website and you can see, like in the bottom left of your browser, it says resolving host, that means it's currently on this first phase of going to the DNS server to get the IP address, because this is also sometimes called a host name. Great, I think it's probably a good place to round this off. If any of it didn't make sense, and I'm absolutely certain that parts of it didn't, I realise the order that I'm doing things in may not be optimal, and I might be jumping past things or going way too quick. What I'm really looking for from you, my wonderful audience, is some guidance on gaps, potential future ideas, anything to kind of fill in this series with details that you will find interesting, and will help you learn a little bit more about how computers operate and make you feel a bit more confident in your day-to-day use of them. Thank you again from myself, and if you're still awake, I hope you're okay. I hope you can find sleep soon, and I will see you again very soon.